Okay, so I think time are passing, so we can start with this particular week dot solving session. So right now we are in the week 5 of this particular week, and we have discussed a lot of concepts, and now the time is to solve few question based on them. But before that, let's see what are the content. Let's see that subtopic that we have covered in this particular week. So here, just like the last week, we were studying about the Sever Plastic deformation, where we studied about the ECAP. This is one of the Sever Plastic deformation technique. So a material which is obtained from this particular the component which we have obtained after the ECAP doing Sever Plastic deformation, what kind of property does it hold? Will it sustain under the wear test or not? Those things we have discussed, that okay, under what condition a particular material can be used and not. So we discuss about the wear test in this particular first lecture. Then we went to another way by which we can prepare the bulk nanostructure, bulk material which can show property of nanostructure. Okay, so here we discuss about the plasma spray coating. And we were very specific that we were seeing the vacuum plasma spray technique. And then after that we discuss about the nano-sized ferroelectric, how the ferroelectric materials are, how they are differing from the ferromagnetic materials, and if we go to the nanoscale, what property, what kind of changes this nano size will affect the property from the ferroelectric point of view. So we have discussed this thing in this particular week. Before I go to the questions, let me ask you that is there any doubt in this particular session, in this particular the concept that we have learned from the videos that was posted on the NPTEL? If there is any, please let me know, we can discuss it. No. Okay, yeah. Okay, then let's move ahead and go to the our doubt solving session. Question number 1. So here is the first question. Let me read it. Which of the following statement is/are are incorrect? Maybe more than one can be right answer. So we are starting with the ferroelectric. Okay, ferroelectric bit can be written with a lower power with respect to the magnetic bits. This is the first statement. That we are mentioning, we are focusing on the lower power, while the ferroelectric bit and then another is the more power. So the point of difference is the power. Like how much power will it take to use the ferroelectric, and how much power will it take to use the ferromagnetic bit? B is false. Yeah, incorrect. So B is the one which is incorrect. And what about the C and D among these two? Ferromagnetic bits are stable in relative large groups. Ferroelectric bits are stable in relative large group. Which one of them will require large number of group of atom or more number of grains for it to be stable? So that is a question. Ferroelectric one will require the large number, right? So in that case we can see that the option D is a correct one. So the ferromagnetic one will require large number. No, this is again a false. So we can say the incorrect answers was B and C. Okay, so now let's go a little bit more deeper in this particular thing. In our microstructure we see grains. Now what is this one bit? How much one bit in the ferromagnetic, let's talk from the point of the ferromagnetic, how much one bit will take? Yeah, so we are discussing right now about the ferromagnetic bits. So we have seen that in the class that ferromagnetic bit will relatively take large number of group of atoms, or not from the atom point of view, we see it will take the relatively large group. We have not specified in what way it will be, right? So how much one bit of information if I want to store in the ferromagnetic bit, how much of space will it take? So roughly, if I tell you, it will take something around the 100 grains. So 100 grains of that region, it will correspond to the 1 bit. That too in the ferroelectric way. Sorry, ferromagnetic. Now what about the ferroelectric? We know it will take relatively large group. Relative to what? Relative to the ferromagnetic. So if I want to store same amount of information in the ferroelectric instead of ferromagnetic, I will require even maybe 200 or 300 grains to store 1 bit of information. Okay, so for example, let us say I am having one hard drive with me, which is of somewhat this shape, usual hard drive, something like this shape, having the particular dimensions. We know that our hard drive, our memory, all the storage devices work on the ferromagnetic. So it was having something dimensions, let us say 6 centimeter, 10 centimeter, and so on and so forth, we can say. If same amount of storage, let us say the one which is I am having is 5 TB. If I want to store same amount of information of 5 TB, instead of ferromagnetic, I want to store in the ferroelectric, the size might get double. The size will be something like half of this particular page, and that's why we majorly use this ferromagnetic bits instead of ferroelectric. Okay, that was the question number 1. Okay, let me know if there is any doubt in this particular question number 1. No? Okay, let's go ahead. Let's go to the next question number 2. A comparatively easier question compared to the question number 1. So which of the following material uses the polarization of atom and molecule to store information? See, polarization of atom. From the polarization point of view, whether it's ferromagnetic, ferroelectric, or both of them, or neither of them use this particular concept of polarization. So from the point of view the polarization of atoms, which so Nisa is telling that it's C. What other? What do you guys think? Whether it's both, or it's ferroelectric, or it's ferromagnetic? When we see the ferromagnetic, we talk about the dipole moment, magnetic dipole. For the ferroelectric material, we talk about the polarizations. So particular atoms is there. What does it mean that polarize? So let us say this is a particular atom and we have applied the electric field. Let us say this was an insulator, insulating material, and here we have applied the electric field. Now what will happen? It might be possible that the center of the atoms will get shifted. Nucleus is somewhere over here and electron are shifted toward the other. So now what this concept is, it's showing some kind of polarization. So the polarization, if we talk about, it will majorly is from the point of view of the ferroelectric material. Dipole moments are with respect to the ferromagnetic. Okay. So here we can say the polarization concept is used by the ferroelectric materials to store the data. Let me know if there is any doubt in this question number 2. Okay, since there is no, let's move to the next question, question number 3. Yeah, here. So this question is telling that ferroelectric properties of BaTiO3. We have studied about BaTiO3. Why the name ferro? Okay, yeah. It is something is coming from the iron. Okay. So whenever we use the term ferroelectric, so initially in the history parts, when the way these things are derived, is it this material always contain iron? No. This material, someone to show the ferroelectric behavior, it doesn't need to be contain the iron in it. Okay. So it's something like what we can say. The concept is derived first from the this particular irons and all. Before the see the ferroelectric properties and ferromagnetic properties, this type of thing, properties was initially first found in the metals. Later on in the, you will be surprised that around 1950s, around those time period, we were getting to know about this thing in the ceramics also. The ferromagnetic properties, ferroelectric properties. Those thing was not there. In from the point of the ceramic was not studied. So the initial study was majorly carried out on the metals, and one of the most popular metal we know is the iron. So from that history it is get carried out, and we are also occupied that particular, we accepted that particular thing. Okay, yeah. So now here ferroelectric properties of the BaTiO3 we have studied. Yeah, so Nisa is telling it's option A. So the question was, and the answer A is a right answer. So the ferroelectric properties of the BaTiO3, we are having this particular material BaTiO3, we know, we have studied in depth about it, are primarily due to the which of the particular things. So we know that in BaTiO3 what is happening. The center of the positive and center of the negative atoms are shifted from each other, and this and because of that shifting, because of that charge separation is the one, because due to the arrangement of atom in such a way that the positive center and the negative center are not lying on, not overlapping over each other, they are shifted. And we know, we have just now studied that whenever there is a charge separation, there will be the polarization, and that is the one which is responsible for the ferroelectric property of it, for the BaTiO3. And that's why we can see that the option A is the correct option, that the arrangement of the atom in the crystal lattice is the one which is leading toward this particular polarization, charge separation, and which is contributing toward the ferroelectric properties. Primary. See, if someone say that okay, no, the presence of impurity atom can also affect, yeah, it can affect. It can also, it can enhance the property of this particular material, it can even degrade the property from the point of view of the ferroelectric. But here the term, the word which is mentioned is a primary. So the main focus we will from where this properties has been arise, we will see from that view. Now the application of the electric field, see, this is the external thing that is applied. Okay, so the we don't need to worry about the, when we are talking about the properties, we shouldn't consider that what is the external things that is applied to it. Now the temperature of the material, is the ferroelectric properties coming from the temperature of the material? That is also, it's not the case over here. It is majorly contributing from this particular rearrangement of the atoms. Now one can argue that okay, if I change the temperature, it might be possible that this particular arrangement might be disturbed. It is very well possible, right? But the property is coming from the atom in the crystals, the way they are displaced. So this is one of the factors that can affect it, but where the property is coming from, it is due to the arrangement of the atoms. So with that we have solved this question number 3. Okay, if there is any doubt, please let me know. Okay, since there is no, let's move to the next question, question number 4. Now it is quite interesting, this question. So see, the some condition is given to us that BaTiO3 is exhibiting ferroelectric behavior. What is its crystal system? We know 7 crystal system, right? Among that particular crystal system, which of them it can be? Tetragonal, cubic, monoclinic, hexagonal. So, what are your opinions on this? Uh, See, let me tell you, BaTiO3 doesn't even exist in the monoclinic. Neither it exists in the hexagonal. These two crystal structure, it's not even existing. It exists in the tetragonal, it exists in the cubic. Okay. But the thing is that if it is showing ferroelectric, it means that what is happening, that the center of the positive and the center of the negative has shifted. Why does it happen? Because along the one of the axis, the crystal has elongated, and since this particular elongated in one of the directions, one of the axis along the C axis, so the symmetry of this is disturbed. Symmetry from from 3/4-fold, sorry, 4/3-fold, 4/3-fold, it has came down to the 1/4-fold. That is, it's only showing the, if I'm seeing from the top, then along this axis only it can rotate about the 90 degree, and so we took the cube, we have pulled it along one of the axis, and cube has transformed to the tetragonal. What about the cube? If BaTiO3 is existing in the cube, what does it mean? It means that the center of the positive and the center of the negative, they are not shifted from each other, they are lying as it is. They are lying onto the same center of the cube. And since there is no charge separation, there will not be any polarization, and so there is there won't be any ferroelectric behavior. So the cubic is the one which is not showing any ferroelectric behavior, while the tetragonal one, which is we have elongated along the one of the axis, is the one which is responsible for the charge separation and showing the ferroelectric behavior. So with that we can conclude that the option A is a right option. Let me know if there is any doubt in this question. Question number 4. Okay, since there is no, let's move toward the next question, question number 5. Oh, this question we have already discussed, but okay, since we have already discussed, I want you guys to answer it. Okay, so the comment on the dimension of the hard drive made from the ferroelectric and ferromagnetic material. So VE is the volume of the hard drive made by the ferroelectric, and VM is a hard drive made by the ferromagnetic. Okay, so Nisa is telling that it's option A. So the ferroelectric is the one which will be having the more volume, right? And that's the right answer. And the reason behind that is because the ferroelectric will be stable over the large group of atoms. So ferroelectric, we know it is stable over large range. So what about if I am giving same amount of let us say for ferromagnetic I am giving hundreds of grain, for ferroelectric also if I am giving 100 of grain, then what will happen? It is very well possible that your hard drive will be crashed. The data which you have stored in it might be damaged and you won't be able to recall it. And so since its stability is not lying into the small range, so we need larger area, larger dimensions to store this particular data, and that's why we got the option A is the correct option. Okay, sufficient data is not provided. No, that is not the case. We are well aware of this. see, one more thing, that in the scientific community, this research has been going on, that how to make use of ferroelectric to a smaller dimension region. Okay, if that can be done, it will revolutionize lot of the materials and the application which we are using right now. Okay. Okay, yes. With that, we have completed this question number 5. Let me know if there is any doubt in this question. Okay, since there is no, let's move to the next question, question number 6. Now, this is something which we have learned in the last lecture of this particular week. Okay, that too at the very end of that particular lecture. So, HFO2 thin film shows ferroelectric behavior because, why is it the case? Why HFO2 thin film is showing the ferroelectric behavior? And one more thing, if I make it thick, then it will not show this ferroelectric behavior. So what are the possible reason which is, so what is your opinion on this, like what can be the right answer? A is a nano effect. Yeah, that is one of the answer, right? So now what is that particular nano effect is something which we need to know. Yeah, so first answer is right. Let me tell you one more thing, that multiple answers are right in this particular question. Okay, it's a multiple selection type. So what is this particular nano effect is happening? High pressure at the small scale leading to the compressive strain. So what they are telling, that since it is thin film, we are trying to make a thin film. So there is a substrate on which we will deposit the material. Okay. So this substrate is having some particular, let us say, some interatomic spacing. Now if I want to deposit my HF2 material onto it, let us say, okay, then what will happen? What has found that the interatomic spacing of the HF2 was comparatively larger, but the substrate on which the particular material deposit is, it is very easy that it should form the bond between them. Then only the structure is easier to grow. Okay. So now what is happening, that this spacing is smaller than this spacing. So what is happening at this particular nanoscale? They are trying to compress. So these bonds are trying to compress this particular. They are trying to make this particular even closer. So while the final structure without any strain, it should look like something like this. So from here it will go to here if there is a thick. But due to the nano effect at the smaller scale, if we make the dimension to be the small, not very large, not very thick, not this much thick, if we make it very small, nano range, then what will happen? This effect of compression will be there. Now what this particular compression field is doing, that is one of the question we need to ask ourselves, right? We have seen the phase diagram, right? We see the phase diagram. What are the variables that are associated with the phase diagram? So what do you think? What are the variables that we usually study in the phase diagrams? If I want to change one phase from another to the another phase, what will I do? So instead that, let me ask you that if iron is there in the ferrite, if I want to convert it to the austenite, what I will do to it? At room temperature I am having the iron. Okay, weight percent. Yeah, weight percent is one of the variable. What about, is there any other variable? So first variable is weight percent. Like if I can change the carbon content in the ferrite. Yeah, temperature is another factor. So in the phase diagram, the normal phase diagram which we studied, we usually see these two factors to affect the phases of the material. But there is one more factor which we usually don't see, that is a factor of the pressure. We know Gibbs phase rule that P plus F is equals to the C plus 2. We usually take this 2 and convert it to the 1 because we say that pressure is fixed over here. Okay, so whenever we are studying our any thermodynamics, any phase transformation that is there in any of your book, that itself there the pressure they have assumed to be the atmospheric pressure, they are not changing it. But now here in our case a pressure effect is there, and that pressure effect can change the phase of the material. Okay, so now we know that G, delta G, which is there, it can affected by is a function of the temperature, mole fraction, and also it is a function of the pressure, and these variables will definitely going to change the Gibbs free energy, and the one which is at the lower Gibbs free energy will be more stable. Okay, so here stabilization of the rhombohedral phase will occur. Okay, so here see HFO2 is usually exists in multiple phases. First one is cubic, then monoclinic, and it is existing in the tetragonal. At the normal pressure, that we are not increasing the pressure, you will see this particular type of phases in the HFO2. But with the effect of the pressure at the nanoscale, the phase of the rhombohedral has also appeared, and this is the one which is responsible. This phase is showing the ferroelectric behavior, because here the charges are in such a way that their center is not lying on top of each other, or they are not overlaying, and that is the one which is contributing toward this ferroelectric behavior. So this is the one. Option D is the correct option. The given statement is incorrect. They are telling that okay, this question itself is incorrect. No, the statement is incorrect. High pressure at the small scale leading to the compressive strain, that is a true, and this is a nano effect, and this compressive strain is the one which is causing this particular phase of the rhombohedral to stabilize, and with that option B is also a correct answer. So A, B and D are the correct answer over here in this particular question number 6. Let me know if there is any doubt in this question number 6. We have discussed lot of things over here. You can recall, and if there is anything that is not a match with your, then you can let me know. If it's something which is difficult to digest, then please let me know, we can discuss it even again. Okay, since there is no doubt, let's move to the next question number 7. Now, one thing about the question number 7, only one answer is correct. So, it is MCQ, it's not MSQ. What is the primary purpose of the Sever Plastic deformation? The primary purpose, why we do Sever Plastic deformation, that they are asking. The first one is to create the porosity within the material. Second, to create the large grain in the material. Third one is to produce a macroscopic sample with a nano-sized grain. And fourth one is to induce the internal oxide formation. So what do you think? Okay, yeah. So Anisa is telling that it's option C. Yes, option C is the correct option. We want the nano-sized grain material, and the sample size will be the macroscopic in nature. We do the ECAP. The material which we get after the ECAP, after multiple passes, it is deformed severely, right? So ECAP is a severe plastic deformation technique, and here we can see that the grain size will be quite refined. While initial grains will be quite coarser in nature. And so we can say that this particular will decrease the grain size. Option B was telling that the larger grain size to obtain. No, uh, severe plastic deformation will never increase the size of the grain. Can you name few techniques by which I can increase the size of the grain? Let us say I am having this particular material. No, I found that okay, no, I don't want this particular grain. I want bigger grains. What kind of techniques I can use? Is there any technique you are aware which can increase the grain size? Yeah, okay. So sintering, yeah, sintering is one of the technique we can increase the. At the final stage of the sintering, we see that there is a grain growth is occurring. Okay. So if I heat it up, the another way to see this, like if I am heating it up, it's an annealing. So by annealing, if I heat up the particular material, what will do, the all the stresses that is and the low angle grain boundary, they will dissolve and they will form the new grains, and the grain will be of the bigger size instead of the smaller size. So option B was incorrect. We are not getting the, from the severe plastic deformation, we are not getting the larger grain size. Create the porosity? No. Our primary purpose is not to create the porosity, not to induce the oxide formation. So that was the question number 7. If there is any doubt, you can let me know. If not, let's move to the next question, question number 8. How many ways we can convert particle into the grains? Okay, that's a good question. So let us say you are having let's focus on this question, that we are having the particles. Okay, let me use one more paper. Only sintering and solidification, or there any other way? Okay, let's say this. So we are having the particle, and we want to convert it to the grain. We want to increase its size. Okay, so what we are doing, we are going from bottom to the top. So this is a bottom up approach. What are the technique that we have learned which can do this part? Okay, so there is one technique we have learned in this particular week itself, like we will provide feed of powder to our technique, and it will deposit onto the substrate. That was the plasma spray technique. So here you will provide some particles with a smaller size, and it will undergo the melting due to the plasma temperature, something around 5000 or 10,000 Kelvin, and then it will be deposited onto the substrate. Okay, that is one thing. When we know the evaporation condensation, that we have usually see this, that nature use this particular type of method to create the nanoscale samples having the smaller grain size, and it can go even further and further. So we can get the later on we can get a bulk sample which is of the nanoscales. So evaporation and condensation is also one of the technique. Then as we have already mentioned that there is sintering. So we are having the particle. So what sintering is about, we have compacted the powders and we are heating it up. So what will it do? It will eliminate this particular the space, that porosity which we are having, and we will form the grain. And one more thing you have mentioned, that sintering and solidification. Solidification is also, yeah. So solidification we can consider. So okay. So these are the few techniques which I am able to recall right now. There might be few more. Okay. So there are multiple way we can do this particular part. Okay. So I think these are the list of the technique that can be used to convert a particle into the grain. Okay. So if there is any doubt in this particular the discussion that we have made? Anisha, Pranav, Sandra, any of you have any doubt, please let me know. So we discussed a lot of stuff. If anything that is difficult to digest, you can let me know. Okay. Okay, so let's move to the next question. I think it's question number 8. Yeah. Question number 8 is quite easy, and again it is a single MCQ type question. So what is the purpose of the pin on disk test? Okay, the answer is B. Quite fast. Answer is B. That's right. So here, pin on disk, we have just discussed that in the class we have discussed that we have obtained the material, we have obtained a pin from the ECAP. If the pin is not obtained, we can change its shape. We can machine it even further and we can obtain the pin. And we'll put it on the disk. And we'll try to we'll rotate it, keep on rotating after multiple rotation and testing after the load which we have obtained, which we apply to it. We'll see how much of the material has gone off, has wear off. Okay, and that is something to measure the wear property, because we know that all the materials, in all the application, most of the application of the mechanical engineering, if we see, one component of the machine is always wearing against the another one, and so wear property is very important from that perspective. So option B is the right option over here. To measure the strength of the material, no. Measure the ductility of the material, no. To measure the yield strength of the material, no. Can you tell me any technique which test can I use to measure the yield strength and ductility of the material? So pin on disk will not tell me about yield strength and strength of the material and the ductility. So which test it is that can be used to measure these three things? Tensile test for the yield stress. Yeah, perfectly right. For the yield stress, we can use the tensile test. Tensile test will also give me the ductility. See, once I did the tensile testing, I can find its yield stress. I can find it UTS, ultimate tensile strength, and I can find how much of this it is showing the ductility to us. And so with that, we can measure all these three things just by doing the tension test. With that, we have solved this question number 8. Is there any doubt in this question number 8? Please let me know. If there is no, let's move to the next question. Okay, since there is no, let's move to the next question number 9. 8 was over 9. This is little bit lengthy question. Just lengthy to read, but it's very easy to answer. What is the relation between the wear resistance with the mechanical properties of the material? So we are having two terms right now. One is wear and second one is the mechanical properties. For a time being, let us consider that mechanical property, we are talking about the hardness. Okay. So what will happen if I increase the hardness of the material? Will the wear resistance will also increase? Question number 1. With the increase in the mechanical strength, the wear resistance will also increase. Is it the case? Second, with the increase in the mechanical strength, resistance to the wear will decrease. Okay, so we are increasing the strength of the material, we are increasing its hardness, let us say, but will its wear properties will increase or decrease? That is the one. Anisha is telling the third one. Wear resistance will depend upon the environmental condition and will differ from the material to material. No direct relation between the wear resistance and the mechanical strength. This is something which this particular entire statement I took it from the word of the our professor Pratap Haridas, and from there I put it over here. So now someone can ask me that why I am increasing the hardness, but still my wear resistance is not increasing, right? That can be the one of the questions. Just a minute, guys. Yeah, yeah. So option 3 was the correct answer. Now, uh, let us say I am increasing the hardness. Why do you think that? Why it is not sure that if I am increasing the hardness of the, I am increasing the mechanical strength, still the wear resistance is not increasing. That is still the more of the, let us say, more wear is happening. Let's try to answer that. So let us say my pin is there, which is very hard. Wear depends on the friction. That is also right answer. Yeah, it will depend upon the friction. Now it is, we are rotating it on the disk. What can happen at the initial stage? Let us say we started rotating it, but none of the material was coming out. Very small, extremely small fraction of the material, because it is very hard, let us say, it is not coming out, but very minute of that particular material has came out. Now my wear, now my the tracking disk is consisting of the abrasive particle which was on the disk, along with that those hard particles which was of the material itself. So now what will happen, both of them will assist this particular wear property. So now what will happen, both of them, that is the debris which is on the, which has came out from the pin, and the one which is on abrasive particles which was already onto the wear disk. Okay, now both of them are increasing the, will lead to the wear. Now my wear will increase even further. So if my material was even harder, then it might be possible that under these circumstances the wear will happen more. Now for the soft material, let us say talk about, if the let us say this was happening, someone telling that okay, what I will do, I will decrease its strength. Let us talk about the metals. I am taking one of the metal, I put it in the pin form, and now what I am doing, I am rotating it onto the wear disk. Due to the friction that you have already mentioned, due to that friction, what can happen, that our metals can oxidize, and the oxide formed will be quite harder compared to the material itself. Now the wear, it will remove the more of the material from the pins, so the wear property, wear resistance will go even down, and we'll see more of the weight loss. And so we can say that it is not related with the these particular factors, it is related with the environmental condition, under what condition we are doing the wear test. Let us say someone is doing the vacuum, they are avoiding the oxide formation, or one can say that it will depend from the material to material also. Yeah, maybe some material which is quite inner toward the oxidation, and the one which is not showing any, like not very hard, and the after debris has came out from the materials, then it's not interacting with the material in the hard way, in the, so it is not increasing the wear resistance. So we can say that it will differ from material to material and condition to condition. So with that, this question we can conclude that option C is the correct answer. There is no direct relation between the wear and the mechanical strength. So if there is any doubt in this question, question number 9, please let me know. Okay, since there is no, let's move to the next question, question number 10. Yeah, so here, so this is, it's quite easy question. We just have to think little bit. With the increase in the cooling rate, the grain size of the material, what will happen to the grain size of the material? Consider the case where we are cooling it very slowly, and consider the case where we are cooling it drastically, very fast. So NISA is telling that there is no effect. So our cooling rate will not have any effect on the grain size. Okay. So this is the third option NISA is going. What about the others? What do you guys think? Will it increase, will it decrease, or what will happen? So now let's see, let's think about it. Since we are cooling it very fast, in case 1 is there and case 2 is there, where we are, first one is slow, second one is fast. So in the slow case, what is happening? We are spending large amount of time at the higher temperature. Okay. In the case 1, we are spending the large amount of time in the high temperature region. Okay, yeah. So the Pranav is telling that option 1 is the right answer. Okay. So it will decrease. Now let's see why it is decreasing. So at the high temperature, we know that nucleation is not favored much. Instead, growth is the one which is dominating. So the nuclei will not form to a larger extent, but the growth, whatever the nuclei has formed, it will grow very rapidly. Now, why nuclei have not formed? What it is that what is the nucleation process? Okay, that is the one thing. So it is like the colony of the, in the liquid state we are having the randomness is there to a larger extent. Let us say I am solidifying it. Okay, after solidification, what we'll get? We will get the crystals, and those crystals, the nuclei of those crystals will form at the lower temperature, right? And so those nuclei, that arrangement of the atom, the small colonies of the atoms which will form on together and which will grow later on, this is known as a nuclei, and that is something will form only at the lower temperature. They will form to a larger extent at the lower temperature. Now at the high temperature, growth rate is quite high compared to the nucleation rate. So we'll see that the grain size will be quite larger if there is if we follow this profile number 1. Large high temperature growth will be there. Now for the second one, we are not spending to a larger extent, we are not spending lot of time onto the high temperature region, we are directly going to the low temperature region to a faster rate. So here we can say that we are not providing sufficient time for the diffusion to occur for it to grow. So here the nucleation rate will be higher, and the nucleation rate is high, and at the low temperature we know growth rate is not very high. Growth rate, that is diffusion to occur, will not be there. To larger extent, the growth rate will be very low, and so at the low temperature we can say that the nucleation is large, growth rate is not high, so we will get the finer grain size. So the grain size will decrease. So the increase in the cooling rate, that is from going from 1 to 2, what we are getting the decrease in the grain size, and that's how we have solved this question number 10. Let me know if there is any doubt in this question number 10. Okay, if there is no, let's move to the next question number 11. Now if you have watched the video of this particular week, then this particular question will be very easy to answer. The cooling rate in the plasma spray technique lie in the range of, so it's just factual thing, if you know then that's it. So then in the plasma spray we know that we are putting the powder, so there is the gun which is generating the plasma 2. Yeah, so option 2 is the correct answer, Nisa, right? So here it is generating the plasma which is at the quite high temperature, something like 5000 Kelvin to 10,000 Kelvin, and from there it is going towards the substrate. The material has already in the liquid form over here, and now they will deposit to the surface. The surface is the one which is we need to cool it down with the time. So it is attached with the liquid nitrogen system, the cooling system. So going from this high temperature to the low temperature of 70 Kelvin of liquid nitrogen, around 70, this particular rate is the one. If you do this, it is going very fast. So at what speed it is going? It is going something around 1 to 3 mesh. 1 to 3 mesh is what is the mesh? Mesh is the velocity of the one mesh. It is the velocity of the sound. So it is related to the velocity of the sound. If I am telling 2 mesh, it means that the particular velocity which we are talking about, that is quite that is like twice of the velocity of the sound. Okay, so it is going at this particular rate. So it's going very fast. Distance is very, so it will cover a small particular distance in a very large, in a very fast manner. It will take very small time. So from this particular temperature, it is going to 70 Kelvin, and it will require something around this particular cooling rate. So that is what the question number 11 is. Okay. Okay, let's move to the next question, question number 12. Which of the following statements are correct regarding the fabrication of the nanostructure using the plasma spray technique? Okay, so fabrication of the nanostructure, from that point of view, see which one is the correct. High nucleation rate with the minimum growth rate, that is the one which is required, or growth rate should be high and nucleation rate should be low, and rapid cooling rate, slow cooling rate. Anisa is telling that it's 1 and 3. Yes. So now these are the correct answer. 1 and 3 are the correct answer. I not even told you that whether it is MCQ or MSQ. Still you have selected the 2 answer and these are right. So this is more or less related with the last to last question that we have solved right now. So if there is a fast cooling rate, we'll get the smaller grain size. Smaller is the better for the nanostructure. Okay. High nucleation rate should be there and the growth rate should be minimum, and this is the one which will favor the formation of the nanostructure. That's the structure having the smaller grain size. Okay, so with that we have solved this question number 12. Let's move to the next question, question number 13. Now it is somewhat a factual type. If you are aware, then we will be able to answer. Pick up the suitable particle size of powder for the plasma spray coating. Okay, so you want to perform plasma spray coating. Your professor has told you, okay, go buy this particular powder, but he not told you about the particle size. So now which particle size you will prefer to buy? And he is telling it's option 3. Yeah, it's the correct answer. So now let's think, the answer is right. Okay, now let's think why only this particular. Why not 10 nanometer? Why not 200 micrometer? So see, if I am going very fine size of the particle, what will happen that those powder which was there, once it get contact in the temperature, what they will do, they will start agglomerating. They will start agglomerating. They will clogging. They will cause the problem of clogging. So the smaller are not preferred. Why larger are not preferred? So now what we have learned that in the last in the last question, in the last to last question, that in the plasma spray coating, first of all the temperature is, it won't melt properly. That is the right answer. So it will melt, let us say, only till this particular region. And the core is not melted up, right? And so what will happen, once this particular particle has reached to the substrate, it will be like the material itself is getting over there. It will not form the splat properly. Okay, and this is one of the type of defect we can say. The particle has not melted and we wanted it to melt. So we will not prefer the higher. So more or less on an average, I think we prefer 5 micrometer to 80 micrometer. This is what we have learned in the class, I think so. 5 to 80 micrometer is the one which is preferred for the plasma spray coating. And with that, we have solved this question number 13. Let's move to the next question. 13 I have printed twice. Okay. 14. Let me mark them first. One. This is the match the following type. Okay. So VR test, among this, which one will be the feasible, proper primary answer you can think of? So for the ECAP and plasma spray coating and tensile test, let's start with the VR test. So VR test will match with the A, B, C or D. Bulk sample that have the nanostructure. Okay, resistance of the specimen toward the VR. So the first one will be marked with the B. Right, Anisa. ECAP. Let's think about the ECAP. Bulk sample that have the nanostructure, stress strain curve or the severe plastic deformation technique. Is ECAP is option D? Yeah, option D is the correct answer for the ECAP. One more thing we can say, to some extent we can say that ECAP can also produce bulk structure that have the nanostructure in it. Okay, that's what we were doing, right? We were putting our sample, which since we were putting, we know that this is having the particular dimensions, let us say dimensions of 6 cross 10 cross 20 centimeter, and from there we are generating the, from the coarse and grain size we are generating the finer. To certain extent we can go with the A also, but primarily we can see that okay, it is a severe plastic deformation technique. Now plasma spray coating, among, so what are left? One is the stress strain curve has left, and this is also to the certain extent has left. Yeah, right, that is right. Option A is the right answer. It will prepare the bulk sample that have the nanostructure. Okay, so option 3 is the correct answer. And so we know that 4 is C. Yeah, tensile test will give me the stress strain curve. With that, we have solved this question. Let's see if I have more question. Yeah, one more question I am having. Explain why ferroelectric behavior of BaTiO3 ceases above its ferroelectric Curie temperature. Okay, so they are telling that I am having the BaTiO3 that was showing the ferroelectric behavior. So first thing I can conclude that okay, since it was showing the ferroelectric behavior, its crystal structure will be tetragonal. Now they are telling that this particular behavior, it is lost above the Curie temperature. Curie temperature is something like around 120 degrees Celsius in the case of BaTiO3. So why it is happening? We are having the same material over here, and over here also we have the BaTiO3 itself, but its property has changed. It's from ferroelectric, it is no longer ferroelectric, it's not showing ferroelectric behavior. Now what do you think, like any rough suggestions you can give, like what might have occurred? This is what scientists do, right? They got some problem, they do operate under certain condition, and then now they will try to think okay, what might have happened, why is the case, right? So let me tell you, over here crystal structure change, yeah, that is the right answer. So crystal structure has changed. Now what was the one that is causing our tetragonal to show the ferroelectric behavior? It was the separation of the charges. The center of the positive charge and the center of the negative charge, they were not lying onto each other. Now we have, since it is over, this particular ferroelectric behavior has ended, it means that the positive charge and negative charge are lying onto each other. It means we are going from to the more symmetrical crystal structure right now. One suggestions we can think from this way, that okay, it might be more symmetrical than tetragonal, and the answer is over here is right. It is converting to the proper cube. So from tetragonal it is converted to the cubic, and here the charges are lying on top of each other, like the center of positive and the center of negative are at the same location, they are not shifting. And so if I heat up, if someone want to degrade the property of the BaTiO3, they just need to heat it up to the 120 degrees Celsius above it, and this particular property will be lost. And with that we have solved this question number 15. Let me know if there is any doubt in this question. Okay, since there is no, let's solve a numerical. Okay, so the numerical is something of this sort. Since we were discussing a lot of things about the BaTiO3, so I thought let's solve one easy numerical which can enhance our particular understanding on the concept of the ferroelectricity. So the question is telling that using the ion positions for the tetragonal BaTiO3 unit cell shown in the below figure, calculate the polarization per unit volume of the material. Okay, so we want to find the polarization. Per unit volume. What is the polarization? We know that it's a summation of the dipole moments. Dipole moments, we know that it's a charge multiplied by the distance separated by them. So Q times D. This is something which we are aware of. Now let's see this question, what it is about. So they are telling that it's a tetragonal BaTiO3. Obviously we know if it is showing the ferroelectric, it should be tetragonal only. Okay, so on to the over here we know that this will be the Ba. At the center it is Ti, and onto the face center we know this is oxygen. Oxygen is having the charge of 2 minus, Ba is having the charge of 2 plus, and Ti is having the charge of 4 plus, and that's why it is forming the BaTiO3. You can see this is plus 2, this is plus 4, and oxygen is minus of 2. We can do the charge calculation, whether it's 0 or not, neutral or not. Plus or on together it's 6, and oxygen we can say that 3 of the oxygens are there and they will have the charge of minus 2. So we can say that total it will be contributing toward the minus 6, and so we can say that overall on an average this particular material is neutral. Now I think that these values are not visible to you guys, so I will tell you one by one. So this particular figure which is over here has seen from this particular view, that this particular plane we are seeing from this particular plane. So this oxygen is over here, this oxygen is over here. So now let's try to find this divided by volume. Okay, first we'll go with the numerator, Q into D. Let's go one by one. See, one thing we need to know, that barium Ba is not the one which is responsible for the charges for this particular ferroelectric behavior. It is the oxygen and the titanium is the one, because they are the one who changes their position, Ba not changes position. So all we need to worry about, the one who displays their position, D value, was the titanium and oxygen. Now let's first of all let's think about the titanium. There is a reference line over here, and we want to find Q times D. Okay, for the titanium, Q times D. What is the charge onto it? Charge, we know it is a plus 4, right? So plus 4 E, okay, is the charge on the electron. Now this has shifted, this particular thing, we can see that I am able to see that over this is a reference line, and it has shifted from this particular reference line which was going through the center. It has shifted by the amount of 0.0016. So here it is written as 0.00006, sorry, nanometer, and it has shifted toward the upside. Okay, now how much of this particular titanium is contributing toward the unit cell? Okay, it is contributing entirely toward the unit cell, that is by the factor of 1. Ba is contributing toward the unit cell by the factor of 1 by 8, right? Oxygen, each of the oxygen is contributing by the factor of 1 by 2. So this was the charge on the titanium, and we know it is contributing entirely 1. So this is over, Q part is over. Now D part. D, we know that 0.006, it has shifted, and it has shifted upward. Let us consider that the up direction is a positive. So here we can say plus 0.006 nanometer. So the titanium is over entirely. There was only one titanium, that too at the center, and we have finished it. So this was for the titanium. Now for the oxygen. Oxygen, let's talk about the face centered one. That is parallel, that not the top and the bottom, not this and this we are not talking about for a time being right now. Let's only talk about the parallel phases one. So we can see that the parallel phases over here, they has displaced in the downward direction, and they have displaced by the amount of 0.006 nanometer. One thing I would like to tell you that I will put the PPT of this particular question onto the website NPTEL one, and from there you can find. Also from the YouTube channel you can click, there will be the link will be provided, from there you can take it. Now the oxygen had displayed by the amount of 0.006 nanometer. What about the charge? What is the charge on the oxygen? The charge on the oxygen is negative of 2e. How many of these oxygens are there? We are talking about one on the back, 2, these are the 2, and these are the 2. Total of 4 oxygen we are talking about. But what are their contribution? Contribution is 1 by 2. This much of the oxygen we are having, and now they are displaced by the amount of 0.006 nanometer in the below direction. So D will go minus of 0.006 nanometer. This we talk about the parallel ones. Okay, now we need to talk about the top and bottom ones. Those are also at the face centered. Their contribution again will be 1 by 2, and they have again displaced in the negative way, negative direction, by the amount of 0.009. So this we will talk about the parallel. Now we will talk about the top and bottom. They are having the charge of minus of 2e, multiplied by how many atoms are there? 2, and their contributions are 1 by 2, and they are displaced by the amount of negative of 0.009 nanometers. This is what we have got. All we need to do, we need to add them up, taking care of the signs. Okay, minus minus will be plus. Okay, yeah, they are having the minus sign, yes, and their displacement is like this. So this will be plus, this will be plus, all are plus. We just have to add the number now. Whatever you will get, put the value of E 1.6 into 10 to the power of minus of 90. Put that and convert this nanometer to meter.